Any electrical professional out there walking onto a fire scene, well, it isn't just another cleanup job. It is one of the highest stakes assessments you will ever make. Seriously, the decisions you make in those first few hours and days after a fire, they determine the safety of that building for years to come. So let's walk through the protocol that protects the property, the people, and most importantly, your license.
This right here, this is the absolute core principle we have to burn into our brains. Just because you flip a switch and a light turns on, it means absolutely nothing about whether that circuit is sound. In a post-fire environment, "it works" is probably one of the most dangerous, misleading phrases you can hear. It totally ignores the hidden damage that can lead to some serious liability down the road.
Okay, let's start with what happens right after the incident. The fire department has packed up, the smoke is cleared, but for an electrician, this is where the real work begins. And the most critical dangers, they're the ones you can't even see. You see, a system that's been compromised by a fire might look totally fine on the surface, but underneath it could be just moments away from a short circuit, a catastrophic failure, or even worse, starting a second fire. Our job isn't just to patch things up and cross our fingers, it's to find and defuse this ticking bomb. Now, the damage really comes from a three-pronged attack. First, you've got the obvious one, right? Extreme heat that melts insulation. But the other two are way more sinister. You have corrosive smoke and soot that gets into everything. And then you have the firefighting water and chemicals. A simple visual inspection, it's going to miss these last two every single time. So let's really dig into the science of soot for a minute. Why is it so incredibly destructive? Because it's not just dirt. It's a fundamental game changer for any electrical component it even comes close to. Soot, at its core, is amorphous carbon. The easiest way to think about it is like a microscopic layer of pencil lead that's now coating everything. And what do we know about carbon? It conducts electricity. So soot creates these invisible little electrical highways where there should be total isolation. It literally turns insulators into conductors. And this creates a dual threat, a real 1-2 punch. First, you've got the conductivity. Those tiny soot particles create little bridges for electricity to cross, which leads to leakage currents and eventually short circuits. Second, you have corrosion. Fires release this nasty chemical cocktail, creating acids that just silently eat away at copper conductors and metal terminals. And that's the really scary part. It's a latent threat, a failure that might not even happen for months down the line. And get this, sometimes the cure is actually worse than the disease. That common ABC dry chemical, that fine yellow powder, it mixes with humidity in the air to form phosphoric acid. This stuff causes what's called stress corrosion cracking in brass terminals. That means the screw head on a receptacle could literally just break off months later. And AFF foam, it's saltwater-based and super conductive. The NEMA rule on this is simple. If that foam touched it, you replace it, period. No questions asked. So, this brings us to the triage phase. As professionals, we have to have a clear, defensible system for deciding what gets replaced immediately versus what we can even think about testing. Your gut feeling doesn't protect your license. A clear protocol does. And our guide for all of this is the NEM GD2 standard. This is the document. This is the industry-accepted guideline for evaluating fire-damaged equipment. So when an insurance adjuster or an inspector starts questioning your decisions, this document is your shield. All right, here are the non-negotiables. We're talking circuit breakers, GFCIs, and AFCIs, your ground fault and arc fault protectors, and surge protectors. If they've been exposed to fire, heavy smoke, or water, they are gone. You can't reliably test or clean their internal parts. That thermal trip unit inside a breaker could be compromised. The sensitive electronics could be fried. There's just no middle ground here. It is always replacement. And you know what? The National Electrical Code backs this up explicitly. NEC 240.88a is crystal clear. You cannot recondition molded case breakers. Trying to clean one up and put it back in service isn't just a bad idea, it's a direct code violation and a massive liability. Okay, so we've replaced all the mandatory stuff. But what about the wiring in another part of the house that was only exposed to smoke? This is where we stop just following rules and we start gathering data. We have to prove that what remains is actually safe. So how do we find these invisible threats? How do you possibly test for damage you can't see, like carbonized soot that's been driven right into the pores of a wire's insulation? You can't just look at it. You need a very specific tool for this job. The best way to think about what we're about to do is like a pressure test for a pipe. An insulation resistance test, which you'll often hear called a Megger test, applies a high DC voltage to the wiring. This pressure basically forces any tiny, invisible leaks in that insulation to show themselves as a measurable drop in resistance. So let's look at how this works in the real world. Performing this test safely and effectively on a job site requires having the right tools and following a very strict procedure. On the job, you're usually going to see two types of testers. You've got your dedicated insulation resistance tester, like a Fluke 1507 or a classic Megger. These are built for pure accuracy. Or you might see an insulation multimeter, like the Fluke 1587 FC, which combines a full-on digital multimeter with the testing function. Both are excellent professional-grade choices. Now, the procedure itself is methodical. You have to follow it exactly. First, and this is the most important part, lock out/tag out. The system has to be completely de-energized, no question. Second, you have to isolate the circuit by disconnecting everything, lights, outlets, appliances. You do this because that test voltage can destroy electronics. Third, for a standard residential circuit, you'll apply 500 volts DC. And finally, you measure the resistance between each combination, hot to ground, and hot to neutral. And here it is. Here's our pass/fail number. The absolute minimum acceptable reading for a circuit you're trying to salvage is typically 2 megaohms. But let's be really clear about this. A healthy modern circuit should read way, way up in the gigaohm range. That's thousands of megaohms. So if you get a reading of just 2 or 3 M, yeah, it might technically be a pass, but it's a huge red flag. It's a sign of trouble. We're almost there. We've replaced what's required. We've tested what's left. Now for the final step. And honestly, this is arguably the most important one for protecting your license: the documentation. Your work is not finished until that report is written. This document is your proof. It's the detailed record of every decision you made, all the data you collected, and your justifications. This is what you hand to the insurance company and the inspector, and it's what you keep in your files to protect yourself. And this report has to be thorough. It needs a detailed inventory of every single part you replaced. It needs your test logs showing the actual mega readings for every circuit you saved. It absolutely must include direct citations from the NEC and NEMA standards to justify your actions. And finally, photos. Photos of the damage before you even started. This is how you build an ironclad, bulletproof defense of your professional conduct. And we'll end with the one code section that just ties this all together perfectly. NEC 110.12b. I like to call it the soot clause. It says that the internal parts of electrical equipment cannot be contaminated by foreign materials, including corrosive residues. Well, guess what? Soot is a corrosive residue. This one single line gives you all the authority you need to reject any component that's been contaminated by smoke. So this leaves us with one last thought. Following a protocol like this isn't just about fixing a building. It's about upholding a professional standard and protecting your entire career. So the next time you walk onto a fire scene, ask yourself, is my process built on hard data and code, or is it just guesswork? Because only one of those will truly keep everyone safe.
Electrical safety and liability. For educational purposes only, this guide is designed exclusively for trained electrical professionals. Electricity is dangerous and can cause fatal injuries or catastrophic property damage if mishandled. Use at your own risk by using this guide. You acknowledge that you are solely responsible for your own safety and the quality of your work. We, the instructor's authors, accept zero responsibility for accidents, injuries, or damages that occur resulting from the use or misuse of this information. Always consult the latest National Electrical Code, NEC, NEMA, and manufacturer specifications before performing any installation or repair. If you are not a qualified professional, do not attempt these procedures.